So does somebody see it? What was the reason for all the H pluses? What do you think the reason for all the H pluses was? It was to form what? Water. And water is a very stable product. Right? That's why all the H pluses. And so can you see the two oxygens there, the high one and the low one? Uh-huh.
Yeah, the one on top wants to use electrons more than the one at the bottom. And then, I mean, this side of the equation. Right? The oxygen wants to use the electron more than the one at the bottom.
That's not exactly the way I was hoping to your phrase. What are you talking about? Oxygen and what? When you say oxygen, I think O2 or O.
So in peroxide, the oxygen is peroxide.
All right.
Let's figure out the electron.
Yeah, or you could put it even more simply. One forms hydrogen peroxide, the other forms water. Which one's more stable, hydrogen peroxide or water? Water. Water is much more stable, so the more favorable one forms water. And so this oxygen is going to act much more strongly than this oxygen, because this oxygen is going to go to the stable product water, whereas this oxygen goes to an unstable product, hydrogen peroxide. And so if there's going to be a reaction, you go like this. We'll talk about that other oxygen later. That other oxygen has to do with reading captions. You know, do you ever read the figure captions in tables? A lot of people don't. You know, they completely ignore the caption. You shouldn't. You should read the captions too. There's a lot of important information in captions. Okay. So let's pick an alternate oxidizer. Some electron poor species. In fact, I'm going to pick a more powerful oxidizer than oxygen. What's a more powerful oxidizer than oxygen? I can pick fluorine, yeah, but I'm not going to pick fluorine. I'm going to pick permanganate. But if I use permanganate, I also should include what? H plus. Why? Form the waters. These oxygens have to go somewhere, as we'll see. And so we mix these. You have to mix these carefully because of this. You know, how strong of an oxidizer is permanganate? It's a very powerful oxidizer. You know, we can see it on the chart. It's number 3 on that chart. It's not number 3 on all the charts because it depends on how comprehensive the chart is. The one in Appendix D of our book is much more comprehensive. All right, now let's take a look at permanganate. What do you think, what structural feature, what property, or what makes you think that permanganate is going to be a powerful oxidizer? What about permanganate makes you think it's going to be a powerful oxidizer, if anything? Yeah, it contains 4 oxygens, but more than that, there should be something else that's even clearer. It's because of the manganese. You know, there are lots of things that contain 4 oxygens. Some amino acids contain 4 oxygens. Some other species contain peroxidase. But it has to do with manganese. What about the manganese makes you think that this is especially electron poor? What was that? What do you mean? It loses all what electrons? All 8? Manganese didn't have 8 to begin with, does it? How many electrons does manganese have? Well, maybe manganese is a bit tricky. I should have done something easier. We look at the periodic table. Manganese is element number 25. So we have this. This would be 1, 2, 3, 4s2, 3d 1, 2, 3, 4, 5. And so manganese has lost all these electrons, the S and the D. It only had 7 electrons in there. And then once it loses all those 7s, then it would be isoelectronic as with argon. And so it would have the core configuration. And so essentially, you could call these all its valence electrons. Technically, that's not correct because these Ds are considered inner shell electrons. The S are considered outer shell, the 4s, compared to the 3d. But it's pretty much stripped all these electrons away. And so it's manganese plus 7. Manganese plus 7 is, how many plus 7 cations do you know of? Not many, right? In fact, none. Why is this plus 7? Well, it's plus 7 because it's stabilized by the oxygens. Okay, that's its parent charge. It's not fully a plus 7. Because we have these oxygens which are minus 2. So there's some electron density to stabilize that. But anyway, we have an electron-rich species and electron-poor species. And then we have some H plus in there. What's the H plus? In this case, going to help us do. It's going to help us form water. It's H plus. We need that. Now, if this H plus were absent, would permanganate be as strong of an oxidizer? If the H plus were absent, would permanganate be as strong of an oxidizer? Would it be equally as strong, or would it be weaker if the H plus were absent? Let's go back to the oxygen. What makes one oxygen more powerful than the other oxygen? What made that oxygen over there down low more powerful than the one up high? Both of them want to react with the hydrogen. Both of them have hydrogen ion as a reactant. You got to explain it in a different way.
The water would be more stable.
What would be more stable?
The water.
Water is more stable than what?
Hydrogen peroxide.
Yes, yeah. Good. That's the way you should explain it. It's forming a more stable product. Hydrogen peroxide is unstable. Water is stable, right? If the hydrogen were absent, what would we not form? Water. Do you think it's going to be a stable? What else could we form that's as stable as water? Anything pop into your mind? So if we didn't have this H plus here, then we wouldn't form what? Water. If we don't form water, we have to form some other product. Do you think the other product will be equally as stable as water? No. And so if we don't have H plus here, will permanganate be as effective of an oxidizer? No. It'd still be a decent oxidizer, but it wouldn't be nearly as effective because we aren't forming the stable product, water. And so we need this H plus here. H plus is going to be +1 oxidation state. And then what we got to do is we got to carefully mix this together. Why carefully? Carefully because a lot of redox reactions are quite violent in nature. And so we carefully mix this, and we just see what happens, you know. And it turns out CO2 gas is generated, and this purple permanganate is converted into a light pink Mn2+. So these are the major products. So this is what we're given. You know, we mix it together and see what happens. You know, oftentimes we got to mix it together because sometimes, you know, if it's mild, you know, if ethanol is mildly oxidized, do you know what forms? Like, for example, if ethanol is mildly combusted rather than vigorously combusted, if ethanol is vigorously combusted, we're going to form CO2 and water. If ethanol is mildly combusted, you know what we could form? Carbon monoxide, incomplete combustion, soot, right? Incomplete combustion. It depends on the conditions. Can you tell me you know what, I want to convert all my ethanol into carbon monoxide, so tell me how I should burn it on the burner. You know, I want this room to fill up with carbon monoxide, so I want to burn this so that it produces just carbon monoxide. Tell me how I should do it. Okay, try it. Close it out, starve it of oxygen. All right, well, this is closed. Fortunately, oxygen's leaking in here. Oh, tell me how much carbon monoxide I'm making right now and how much CO2. Is that something that's easy to do? No, and so a lot of redox reactions, it depends on the conditions, you know. I don't know how much carbon monoxide. Here I'm generating very little carbon monoxide, right? Here I'm getting the yellow glow. The yellow glows, you know what the yellow glow is from? Soot particles, you know, just carbon particles glowing in the heat, right? And so I know I'm producing soot. I must be producing carbon monoxide and maybe some CO2 as well. I got to be producing some CO2, it looks like. And so oftentimes with these redox reactions, and you know, there's so many variables in how you do the reaction, the temperature, the pressure, all these things are variables. And so that changes what the product is. And so the skeleton is you just mix it and see. Well, this is what happens. Under, well, permanganate's a strong oxidizer, but under milder conditions, you know, milder conditions, you might not get CO2. Under milder conditions, you might get something else. You know, have you ever heard of wine turning into vinegar? You heard of that? My first experience with wine turning into vinegar was I was on a camping trip in Joshua Tree and stopped by the, I think it was the dollar store someplace in town of Joshua Tree. And they had Santa Barbara wine on sale. And I thought, wow, Santa Barbara wine. Because from Santa Barbara, so. And it was only $1 a bottle. It was a $1 bottle of Santa Barbara wine. So bought a bottle, took it back to the campsite, and then took one taste of it. Vinegar. You know, I had to spit it out and threw it away, and ended up wasting $1 plus tax. But it was bad. What happened was the ethanol was mildly oxidized to acetic acid, vinegar. It tasted awful. Gave me a headache too. you know, and I had to, I mean, if you drank it, because otherwise you're going to waste the money, boy. I was tempted, but God, enough. So anyway, we have this, and so we see, well, what kind of conditions will generate vinegar? Well, certain conditions do, you know, just a little bit of oxygen must have gotten in there, right? And oxidized the ethanol. But it didn't burn it to CO2, it didn't burn it to CO, it didn't burn it to soot, just converted it into acetic acid. All right, so how do we balance those types of things? Because that's what we are going to do. You know, we know what the products are. You know, the reaction occurs. There's a driving force is present in this. How do we know a driving force is present? Because something happened. You know, we saw that there was a change, and we saw what the major products. All right, so balancing the reaction, we have to split it into half reactions first. So we'll just go ahead and do that. CH3, CH2, OH gets converted into CO2. That's one half reaction. The other half reaction is the permanganate changes to Mn2+. I could include the H+ in there, or I could just leave it out. H+ and water always balances in these, so usually I choose just to omit it. All right, the way we balance these is we balance all elements other than hydrogen and oxygen, so the 2 carbons here, and then 1 carbon over here. And we balance that by changing the coefficient here, so we need to add a 2. Then we have 2 carbons on both sides. Then we balance the oxygens. We have 1 oxygen over here and 4 oxygens over here. And the way we balance oxygens is by adding waters. We got 3 waters. Then we balance out the hydrogens. And so it's 6 plus 6 gives me 12 hydrogens on the left, and then 0 hydrogens on the right. The way we balance those is by adding 12H+. Okay, then we'll balance the charge. The charge is going to be 0, and 0 gives me 0. This is 0, but that's plus 1 times 12 gives me plus 12. And we balance this by adding negative charges, the electrons. So we'll add 12 electrons here. So that should be it. Okay, do you know what we call this here at the top? We call this a balanced reaction, balanced redox reaction, or balanced half reaction. This should be a balanced half reaction here. And so the end result of this should be a balanced half reaction. The reason, does somebody know why they call it a half reaction rather than a full reaction? Yeah, that, and there's another reason. The other reason is this, is the product here, 12 electrons. Can I just go ahead and do this half reaction and bottle the 12 electrons, just capture it in a beaker, put it in a jar and seal it? Can I have a bottle full of just electrons alone? No, it's too unstable. It'll generate huge voltage. That would be incredibly unstable. And so these electrons, these free electrons, are too unstable to exist as free electrons. And so those have to go somewhere. Where they go is to the other half reaction here. And so let's do the other half reaction. And so we have 1 manganese, 1 manganese. And so the manganeses are balanced. And then 4 oxygens, and no oxygens here, so I need 4 waters. And then let's do the hydrogens. 0 hydrogens on the left, 8 hydrogens on the right. And so I'll need 8 H pluses over here. Just add it like that. And then the charge. Plus 1 times 8 is plus 8, minus 1 is plus 7 on the left, plus 2 on the right. And so I have to add negative charges, so it's going to be plus 5 electrons. Plus 5 electrons will give us minus 5, plus 7 is plus 2, plus 2, and plus 2 match. And so this would be the other half reaction. I should have given myself a little bit more room. All right, so we have the balanced half reaction here. This is going to be the other balanced half reaction. Let me rewrite these. What I should do is I should double check that they are indeed